So.
Okay, so we have some homework due today, and I realized somebody came by my office and asked me some questions about this, about a homework assignment that this program that I just skipped through it, not thinking that it's a little bit necessary for you to understand how to do one of these homework exercises. So before I ask if there's any other questions, let's take a look at figure 2.25, which is this program to do the following. You see the input-output at the bottom there? It says enter 4 integers, 3, 2, 6, 4, and then it says their sum is 15. Well, I mean, obviously one way to do this, the simplest way to do this is with a loop. But we'll do this using recursion just to illustrate, one, how recursion works, but I mean, you already know how recursion works. But two, another principle is that what this program does is it passes an array as a parameter. Now, you all remember from C++, this should be review, that when you pass an array as a parameter in C++, it is always by default, even without the ampersand, it is what? It's called by reference. This means that all the cells of the array are not copied onto the runtime stack when the function gets called with the array as the parameter. Are you with me?
Is that only when it's global though?
No, that's always.
So that's the difference between the array being a local variable and the array being an attribute?
Okay, when you use the word attribute, we're not talking anything about objects here. The C++ memory model that we are using is not object-oriented.
Right.
So we have no classes here.
Not attribute, parameter.
Okay, now ask your question again so I can remember.
When it's a local when the array is a local variable, then all the cells are on the runtime stack. But if it's a parameter, then they're not.
No, let me say that again. What happens is every time you pass an array as a parameter, regardless of whether the actual parameter is local or global, the formal parameter is always a single pointer back to the first cell of the array. Now the thing of it is that it can either point back to the first cell of an array, of a global array, or it could point back to the first cell of an array that is a local array. In the first place, in the first example, it would point back to an array that's in a fixed location in memory, and in the second case it would point back to a fixed location on the runtime stack in the main program.
So it would just point to the first cell?
Yeah.
Okay.
That's the way it always works.
And then any changes that happen within the program, they change on the bottom of the stack?
Yeah, well they change wherever it's pointed. Not necessarily the bottom of the stack, it could be, the actual parameter could be a global variable.
So, but in the program, if you're calling like the third cell, but it's pointing just to the first cell, right?
Yeah, that's right. Yeah, that's right. It's just like you would, it behaves just exactly the way you would think it would.
Okay.
Yeah. All right. So let's take, so I just rushed through this figure last time and didn't realize it was going to be, that I was skipping this material. So let's just take a look quickly at what the runtime stack looks like. Now in this figure, which is figure 2.25, where we have an array called list. Is it local or is it global?
Global.
It's global. Therefore, where is it allocated?
At a fixed point.
At a fixed location in memory, according to our C++ memory model, which we can review as, what's the first one? Globals are stored at a fixed location in memory.
The local.
Locals
On the runtime stack.
on the runtime stack. I should emphasize it's not only the locals, it's also the what? On the runtime stack.
Parameters? The parameters?
Parameters, yeah. I should say locals and parameters on the runtime stack. And then the third part of the memory model?
Is
Dynamically allocated variables allocated from the heap. Okay, which is separate from the fixed location. It's separate from the runtime stack. Are we good? Okay, so in this program, we have the global variable list for, and now it says cout, enter 4 integers. And we go cin, list sub 0, list sub 1, list sub 2, list sub 3, so the user enters 3264. And then cout, their sum is, and now, what is it saying? It's saying their sum is, and it's calling sum, which is a function. And what type does it return? An int. So that's the ret val. So what things go onto the runtime stack? The ret val, then what?
You have the parameters.
Is that what's, is that what's?
It's the parameter.
No, we're calling, the main program is calling this one. It's calling sum. So first the ret val,
And then the parameter.
then the parameters, which in this case, how many parameters?
2.
2. Right? And then what's,
Return address.
then the return address, which in this case is going to be what? RA1. And then what?
The local.
Local variables. Does this have any local variables?
No.
No. And then it says if n equals 0, return a sub 0, right? Else return a sub n plus the sum of a n minus 1. Okay? So now when you, so here in figure 2.26, we said 4 things would get allocated onto the runtime stack, right? 5 normally, but 4 because this has no local variables, right? So, and notice that, okay, the storage for the ret val, and part B of the figure, storage for the ret val, and then A is the array. But notice that A, it's not all 4 cells. It just points to the list in the global list. Now, I grant you that this is not actually, doesn't look like it's pointing to the first cell of the array, it's pointing to the whole thing.
Right.
So for now, we'll just ignore that detail. Later, when we redo this in assembly language, we'll see that it's going to be important that it actually points to that first cell. All right? And then when it calls itself recursively, A is the formal parameter, and it's also the actual parameter. So the A up here on the second stack frame refers to that same A, so they're both referring to that. Now for your homework assignment, I think what happened was your array was local. So instead of having this up on the stack frame pointing to a global thing, it points down, it'll point down to the first cell in the, on the runtime stack. So is everybody?
And that first, it's only one cell in the runtime stack, it's not an array of cells?
It is an
It is
array,
an array. Okay.
of cells, yeah.
Okay.
Yeah, you know, maybe when I do this again, maybe on the next edition, I should have those cells be individual and have it point to the actual first one. I should probably do that next go around.
You mean on the 3264?
Yeah, yeah. I think it would be, but I think it would be. Yeah, I should do that. 5th edition, because that's closer to what it actually is, and that's closer to how we actually do it at the assembly language level.
So for the homework problem, do we need like a first,
On the homework problem, whenever you set up an array on the runtime stack, you know, it'll be like this. This one will be, there will be a sub 0 and a sub 1, and it'll be like this. It should look something like, oops, about to fall over and break my neck here.
do we need a stack frame for the main program then, and that's what it's pointing to, is that stack frame, or is
It is the stack frame of the main program.
Okay.
And now, and then I said that what we're going to do, just for, so we wouldn't have to keep, I mean, just to keep the figures simple, we will it's okay if you omit the ret val, the int ret val of the main program, and the return address to the operating system. So we will typically just not even bother putting those on the figure, even though we know they're
Or
there.
if we need like an array from the main program.
But if you need an array, whatever local variables, whatever local variables, you need to include those, all the local variables of the main, and they are on the runtime stack for the main. So, but it's okay if you omit that int and the, you know, Okay, so are we good? Any more questions about the homework? We got a lot to do today, so. Yeah.
Return addresses? Did you want to ask about
Oh,
those?
yeah. The one that we talked about earlier.
Oh, you know, there's a typo in the book that actually, one of you guys have already got bonus point.
Oh, really?
Yeah, there's a typo in the book. What is the figure? It's on the webpage now. I just updated the webpage, the errata sheet on the webpage. But yeah, I've assigned this problem many times before, and no other student. Which exercise was that? 8.
2.8.
On 2.8, the return address in the main program called RA1.
Should be 0.
No, it should be RA1, but it should come right after the call to what instead of, in other words, you need to switch the position of C out and RA1.
I have another question about this assignment. I'm not looking at it right now, but isn't the array initialized to have 5 slots?
In this problem?
Yeah.
It is, and the reason it's
And then it only fills in 4 of them.
well, the reason is because whenever you do that assignment statement into an array of care, the in C++ there is a sentinel value, which is bash 0
At the very end of
at the
it.
very end,
Oh, okay.
and so you need that slot for that.
Do you want us to put that on the runtime?
Yeah, I don't care if you put that down or not. Yeah, it's bash 0. Yeah. That's a standard. That's an old C string. Frequently these days, when you're using some IDE, you use a library and you use the library's string. Like when we do Qt, we always use QString. So, and then that has a whole bunch of other features. And anyway. But this is kind of like a raw C. The way it works in just raw C++ is it's a string of 1-byte characters and then terminated with bash 0. Okay. So, information representation. All right. Now, here is the story with information representation. All information at the machine level and at the instruction set architecture level. Which level is that? Have you memorized your levels?
About 7?
There are 7 levels altogether, but which one is the instruction set architecture level?
I'm going to go with 3.
4.
5.
3, 4, and 5. Do I hear 2? Going once, going twice. Yeah, it's ISA 3.
Yeah.
ISA. We're gonna abbreviate this. Have this abbreviation with this digit. Okay, so ISA 3. All right. So at the instruction set architecture. Oh, what does ISA stand for?
Instruction set
So at the ISA 3 level, all information is stored in binary. Binary, bi means
2.
2. So the 2 values that are represented on paper as
0.
zeros and ones. Although inside the computer, it's high voltage level, low voltage level. That's what it is inside electronically. There's obviously not a little man in there with a piece of paper that's writing ones and zeros down. Okay? So now, the first big concept that we have to understand is that every data value is stored in a group of bits. And that group can be anything from 2 to 3 to 8 to 16. It can be the size of the cell that contains the information, depending on what part of the computer you're talking about, can be any arbitrary number of bits. Are you with me? So what we're going to do is we're going to learn general information storage principles, binary information storage principles, and when we do this, we will always assume, we will always say how many bits the cell contains. Are you with me? So this first example we're going to do shows a 7-bit cell in figure 3.1. So each one of those cells can contain either a 1 or a 0. So in part B of the figure here are some possible values, right, of a 7-bit cell. We just got random 1s and 0s there. Yeah? Are you with me? Now, tell me, why in part C of this figure, why is the top example not possible? Why is that top one impossible?
Not 1s and 0s.
They're not 1s and 0s. And what about the second one? They're not ones and zeros. And what about the third one?
There's blanks.
Yeah, and here's another point. Electronically, when you turn on the computer and it's running, every cell has a value, either a 1 or a 0. It's impossible for it can't have no value. It's impossible for it to have nothing. It will be either a 1 or a 0. Now, you might not know what it is, but it will be something. Do you see what I'm saying? So when you turn on your computer, like your computer's off, and the first thing that you do when you turn on your computer, now, what were the 4 parts of a computer?
Like a bus?
No, that's not one of the 4. What is the bus?
The bus is a group of wires.
Is a group of wires. But now what are the 4 parts?
The input,
The input,
the memory,
the CPU,
main memory.
the main memory,
Output.
and the output. When you first turn on your computer, that main memory, when it comes up from the power off state, all those bit values in there all come up at random. But they are random, you know, they are random values. And then in the boot up process, either taking the information off your hard drive or from a read-only memory or whatever, then the memory, the data that gets loaded into the memory at run, you know, when you boot up, you know, all your programs and your operating system, and then they have the values that they need to have in order to run the computer. Are you with me on that? You see how that, you have a feel for how
The
that...
memory is physically stored in like your RAM sticks, right?
Yes, the main memory. Right. Okay, now, first thing we have to do is we have to learn how to count.
Good.
Now, here's a little table of how to count in decimal. Now, do you see how this works? Let's start at the beginning. We start at 0. So we go 0, 1, 2. Now look, it's 0, 1, 2, 3, 4, 5, 6, 7, 8. But now, what happens when you get to 9 and you want to go to the next number up? You know, why do you suppose that when we get up to 9 and we want to go to the next number, we don't just invent a new symbol?
We shift, because it's...
Why do you suppose that we do that? Why do we suppose we do
In our
that?
hands.
It's probably because of our hands. I mean, think about it, right? I mean, historically.
Why would we choose 10?
Well, I mean, when you run out, when you're at your last digit, when you're in your last digit of your hand, you know, we say, well, you know, what you do is you use the first 2. You use the 0 and the 1, you put them next to again, and it makes 1, 0. It makes 10. And then 11, 12, 13, 14, 15, 16. Now, then once you get up to 1, 9, the 9 is as high as you can go. So what happens to the 9? It goes to 0, and then the other one goes up. So everyone knows how to count in decimal, right? Now, what if when we were evolved or were created or whatever, we didn't have 10 digits in our fingers? What if we had 8? What if we had 4 on each hand? Then what would we have done? We would have got 0, 1, 2, 3, 4, 5, 6, 7. But now we're at our what? Our last digit. So what would we have done?
10.
1, 0. Well, yeah, I kind of hesitate to call it 10
Yeah.
because it's 1, 0. It's really 8, but the value is 8. It would be this many.
Yeah.
Is everybody clear on that? And then it would be 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. But now when we get to 1, 7, what's the pattern?
Go to 2, right?
Yeah, the 7 goes down to 0 and the 1 goes up to 2. But now you got to be careful because what happens if you get to 7, 5, 7, 6, 7, 7?
Then you have to do 1.
You need a
Then,
0.
yeah, then you go 1, 0, 0. Does everybody see how that works? All right, and then 1, 0, 1 and 1, 0. We got to be able to, so this is base 8. Base 8 is called octal. Okay? And we will abbreviate it like this. Oct, all right? And we will abbreviate decimal, DEC. Okay, so that's counting it out. What if we had just one arm and that arm had like 3 fingers? What would we do?
There's 3.
So how would we count?
1,
0, 1,
1, 0.
no,
2.
with 3 fingers.
0, 1, 2.
0, 1, 2,
1, 1, 1, 2.
0, 1, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, 1, 0, 0, 1, 0, 1, 1, 0, 2, 1, 1, 0, 1, 1, 1, 1, 1, 2. Does everybody see how this works? And you see how what happens when we get to 2, 2, 2?
1,
We go up to 1, 0, 0, 0. How many fingers does a computer have?
2.
2. So now you tell me, can you count? Can we count?
Yeah.
Okay, so 0.
1.
Okay, let's go around the room. I want to go around the room. Boom, 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 boom. All right? Okay, here we go.
Do I start?
Yeah.
1, 0.
1, 1.
1, 0, 0.
1, 0, 1.
1, 1, 1. 1, 0.
Does everybody got it?
Yeah.
1, 1,
1, 0, 0, 0.
1, 0, 0, 1.
1, 0, 1, 0.
1, 0, 1,
1, 1, 1, 1, 0.
1, 1. What did you say?
Wait.
Wait, yeah. What did you say? Yeah, okay, okay. 1, 0, 1, 1. What's the next number?
1, 1, 0, 0.
All right.
Yeah.
Okay.
1, 1, 0, 1.
1, 1, 1, 0.
Yeah.
1, 1, 1, 1.
1, 0, 0, 0. 0? 4 zeros.
4 zeros.
1, 3, 0, 1.
1, 0, 0, 0, 1.
3.
1, 0, 0, 0, 1. Okay, come on.
1, 0, 0, 1, 0.
1, 0, 0, 1. Okay.
1, 0, 0, 1, 1.
1, 0, 1, 0, 0.
Okay, yeah. One more.
Okay. 1, 0, 1.
1, 0, 1, 0, 1. Right? Does everybody see how that worked? Okay, that's counting in binary. Here it is. Now look, you guys. How big is this number right here? 1, 0, 0, 1, 0, 0, 0, 1, 0. How could you figure out how big that is? Well, one way to do it would be to do what? Go.
Power of 2.
Well, I mean, you could go back. Which one? This is on the 1, 2. That's in this position. We could go back to the decimal one.
34.
Oh,
It's 34. I mean, you could just count, right? I mean, like this. You could just count, right? But obviously, what do we need to do?
No,
We need to know how to do what? Convert from
binary.
from binary, the values from binary to decimal and decimal to binary. Okay, now, so before we do that, here is in figure 3.2, here is the place values. Now, this is completely analogous to the place values for a decimal number. I think the next one is a decimal one. Yeah, see here we have the decimal number 58,036. And so you know that the right-hand side is the ones place, the 3 is at the tens place, the 0 is at the hundreds place, the 8 is at the thousands place, and the 5 is at the 10,000s place. So what's the rule? Each time you go one place to the left, what are you doing to the place value?
10 to the...
Multiplying it times 10 from the one that went before. So what's the rule for power of 2 in figure 3.2 here? It's the 1, instead of going 1, 10, 100, it's 1, 2, 4, 8, 16s. Does everybody see how the place values work in binary? Okay. Okay, and so this tells us then how, this is the basis of how to go from a big binary number to decimal. So let's do an example. So here we'll do binary. Binary to decimal. So here's the one. 1, 0, 1, 1, 0, 1, 0, 0, 1, 1. Over here. So, how would you, what decimal value is this?
1.
Well, it's 1 plus 2, here, it's 1, 2, and this is 4, 8, 16. Now we don't, okay, 16, 32, 64,
128,
128,
256,
512.
256.
Oh, but there isn't a
There isn't a 256.
Oh, sorry, there is no 256.
So 512.
512, is that what it is? 1 plus 2 is 3 plus 6 is 9, 13, 23, is that right? Carrier 2, am I doing this right? Are you with me? Oh, wait, are you with me? I hope I'm doing, you need to check me this, I don't have any notes.
Carry the 2.
Carrier 2,
129.
6, 7, 8, 9, 10, 11, 12, 1, 2, carry 1, 5, 7, 723. Now, is this number, if I just gave you 723, how would you know if it's even or odd?
You look at the last digit.
Last digit. If I give you a binary number, how do you know if it's even or odd? You look at the last digit. If it's a 0, it's what? If it's 1, it's odd. Are you with me? Because all these other ones that you're adding are even numbers. So you're going to add a whole bunch of even numbers to the last one, which is either... Is everybody good? Now, how about the other way around? Suppose I give you a number like 563.
Something odd.
Now, I want you to tell me... Yeah, well, you guessed the first digit. Well, it's odd, so the right one was 1. But now, how are you going to figure out the digits?
Isn't it easiest to
You
start
take the
from the left?
highest, so you got like 500.
You find the biggest power, so we start at like 512.
Yeah, that's what you could do. Well, that's what most people do, they think of when they see this for the first time. What you do is you could look at the powers of 12, but then what you have to do is you have to figure out the power of 2 that is
Just beneath.
less than this, but double is not greater than this.
Right.
All right?
That's not that bad.
And then you would subtract 512 from this, but then what would you do?
And then you
Do
have
it
to
again.
add that
On the next one.
Well, I know, but yeah.
With the remainder.
Yeah, and then you'd have to think, okay, powers of 2. Okay, now, do you want, okay.
Is there a better
Now,
way to do it?
there is much better. I'm glad you asked. Watch, this is slick. Watch this. Watch this. This is going to be very slick. What you do is the following.
Oh, yeah, cut them.
Now watch.
Fancy.
What you do is you take 563 and this is really easy to do in your head. You divide it by 2. Now what's 2 into 563? No, it's very easy. 2 into 563 is what?
281.
It's 281 and what remainder?
1. That's not the first digit or the last digit?
What do you think? Now what do? You take 281 and do what? Divide it by 2. So it's 140 with a remainder of 1. Now what's this?
70.
70 with a remainder of what?
0.
0.
35.
35, 0,
17. 1.
17, 1,
8. 1.
8, 1,
4 0.
4, 0,
2 0.
2, 0,
1.
1, 0,
1. Or 0, 1.
0, 1. And what do you think you have here, sports fans? But which way do you write it?
From top to bottom.
Probably bottom.
Which one told us that it was odd? Which one told us that it was odd?
The first one.
This one told us that it was odd. So this must be the what? The left-hand side or the right?
The right hand.
Yeah, the right hand, the least significant bit. So the number then would be is 1 0 0 0. So it's 1 0 0 0 1 1 0 0 1 1. And you could double check this by, shall we double check this? By going the other way?
Sure.
Okay, so what do we have here?
1 and 2.
1 plus 2,
And
4, 8,
16 and 32.
16 and 32,
12.
and 5, 12.
There's 13.
6, 7, 8, 9, 10, and 13. 3, 4, 5, 6. 563. 563.
You know.
Now, is that slick?
Yep.
That's a lot easier than.
Yeah, I mean, it gives you the bits right off the bat just from the remainder.
How come we weren't taught that way?
I'm teaching you that way. Right? What I'm saying is that's how to do it. Here's figure 3.4 is the polynomial representation, powers of 2, powers of 10 for decimal, powers of 2 for binary. And here's 22 done using this little algorithm, right? Is everybody good on how that works? So now I have a question for you. Now we know how to count and we know how to convert from decimal to binary and binary to decimal, but we are assuming I should maybe prefix this with the preface this with the fact that we are assuming unsigned values. Now here's what we have to do. How many cells, so what is this number here? Oh shoot, I mistakenly.
22.
Is that what that is? Is that the 22 from our other one? Now, so how many bits do we have in this cell? 7. Now, so my question now is, what's the smallest number that we can store in a 7-bit cell? 7-bit
The least value,
cell. Yeah, the smallest number. 7-bit cell.
if they're all.
The range. Now, what I'm asking for is the range of values that you can store in a 7-bit cell. The smallest is let's write it in binary. In binary, the smallest is what?
0.
2, 3, 4, 5, 6, 7. It's this.
Unsigned, right?
Unsigned, yeah. This to what? What's the biggest?
1, 1, 1, 1, 1, 1.
Okay, and this is what we'll abbreviate this binary. We'll call this binary. And then, but now what are these in decimal?
0.
This one is obviously 0. 0 to, now what is this number?
Big.
Oh, come on, must be.
It's 1 less than 2.
It's 1 less than, okay, this is 1, 2, 4, 8, 16, 32, 64.
Never mind.
64, the next one is 128, so it's 1 less than 128, so it's 127. Now, does everybody see this here? Are we good? Okay. Okay, so that's this is how we determine the range of cells, or the range of values, of unsigned values in a 7-bit cell. You just write down that in binary and you can convert. Yeah? Are we good? Now, the next thing we have to understand how to do is how to add. So what are the rules for binary addition? Well, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. But what's 1 plus 1? It's not 2, it's what? It's 0, carry the 1. Now, does everybody see that? Are you with me on this?
So, because it's like 1 plus 1 is 2.
1 plus 1 is 0, carry your 1. That's how it works. That's how the computer actually does it in the CPU. All right? Are we good? So let's do a 7-bit cell. Let's do 1 0 1 1 1 0 1 0 0 1 0 1 1 1. And let's do, now the way we're going to do this is we're going to say add. All right? So let's see if we can add this correctly. What's 1 plus 1?
0.
0, carry your 1.
Yeah.
Now, 1 plus 0 plus 1 is
0,
what?
carry the 1.
Is 0, carry the 1. But now 1 plus 1 plus 1 is what?
Carry the 1.
Is 1, carry the 1. Are you with me?
Yeah, okay.
And then 1 plus 1 plus 0 is what?
0, carry the 1.
0, carry the 1. 1 plus 1 plus 1
Carry the 1.
is 1, carry the 1. 1 plus 0 plus 0 is what?
1.
1,
Then 1.
carry the 0. You carry nothing, right? And so 1 plus 0 is 1. Now, does everybody see how that worked? Now, you want to check it?
Sure.
What is this number? Okay, Ben, you do this number. Ashley, you do this one. You do this one. Okay? You do this one.
Oh, God.
Just convert. I want you to convert this to decimal. You convert this to, okay? So what do we have here? Okay, first one.
29 plus 64 is
Come on.
93.
Say it again.
93.
93. Next one.
23.
23.
156?
156. Is that right?
Wait,
No, something's off.
I got it wrong.
Maybe 116.
Okay, better. Okay, we have. Okay, let's find out. Do this one.
Oh, 11. It's 1116.
116. There you go.
116. Okay, now is that right? Yeah, 6, 9,
Yeah.
yeah, okay, so that works.
I was thinking horizontally instead of vertically.
Oh, yeah, that would make a difference.
I was about
Okay, now I have another question for you. How about, let's do another one. Let's do, okay, over here. Let's do 1, 1, 0, 1, 0, 1, 1, and 1, 0, 1, 0, 0, 0, 1. And let's do add.
We're gonna run out of room.
What do you think is going to happen? Okay, so now 1 plus 1 is what?
0 carry the 1.
0 carry the 1.
0 carry the 1.
0 carry the 1. 1. 1. 1. 1.
0.
0, but now what's the problem?
We don't have enough space.
We don't have enough space. So now we have to understand what happens inside the computer whenever there is not enough room to do the result of the addition.
It explodes.
No, it does not explode. Yeah, that would be unfortunate because if you added a really big number, all of a sudden you go. Okay, here's what happens. There is a special bit. Oh, by the way, first of all, what are the 4 parts of a computer? Input, CPU.
Main memory, output.
Which of those 4 components do you suppose this addition takes place in?
CPU.
The CPU. Inside this,
And the register?
there is, well, that would be a 7. That could be a 7-bit location inside the CPU, and it is called a register. Now, so now, you guys, there is a special bit location inside the CPU that is reserved for storing the carry out. That's called the C bit. Are you with me? Is everybody clear on that? That's called C. So what would happen here is this would be C equals 1. And in fact, even in this first situation over here, the C bit is set because what gets carried out in this case? 0. So here it
Everything
is.
is set to something.
Huh?
Everything is set to either 0 or 1.
What was it again?
Yeah.
Okay. So does everybody see how that works? So anytime you do an addition, the carry bit is set and it stores and why is that? The reason they do that is because if you're adding 2 unsigned numbers, you don't know, even though each of these individual ones might be in range, the sum might be out of range. So it's up to the software. There is a special instruction in the instruction set. What level are we talking about here? ISA 3. There are instructions in the instruction set of an ISA 3 at the ISA 3 level of a computer to test the C bit. So it's up to the software to check to see if there was an overflow. Are you with me? So when you write an assembly language program or whenever the compiler converts an assembly language, then that's what it has to do. I mean, yeah? Okay, now the question comes, how are we going to store a negative number?
Well, I doubt we put a negative.
So here in figure 3.7, let's instead of moving from a 7-bit cell, let's suppose we have a 6-bit cell. My question is this. Question: how to store -5? Right? Now, if I told you that we had a 6-bit cell and I said to store 5, how would you store 5? Okay, so positive 5.
1, 0, 1.
Positive 5 stored would be stored how? How would positive 5 be stored in a 6-bit cell?
0, 0, 0,
0, 0, 0, 0, 1, 0, 1. Now, does everybody see that that's how positive 5 would be stored in a 6-bit cell? So how would you store -5? Well, why is that impossible? Why is figure 3.7 impossible?
It only reads 1 and 0.
Yeah, you can't have a negative sign inside the cell. So what do you suppose they do? What do you suppose the engineers do? How are we going to solve this problem?
They add a
Do they
bit.
put a 1 there and have it interpreted as a negative?
That's exactly what they do. Did everybody hear that? What you do is you reserve this part of the value. This is reserved as the sign bit. Reserved as, it's called the sign bit. All right? So now, do you see that by reserving the first cell as a sign bit, now we can't store as high a positive values anymore, right? What's the highest number that we can store in a 6-bit cell if we are interpreting the data as being signed? This would be 1, 2, 4, 8, 16,
Yeah. 31.
31. Yeah, 31 would be the highest number we could store instead of 63, which is the highest value we could store if this were not reserved for the sign bit. Is everybody clear on this? So how do you think -5 is stored? Okay, now I will say this is how +5 is stored, because if the sign bit is 0, this is positive. Now here's my big question to you. How is -5 stored?
1, 0, 0, 1, 0.
You would think that it would be 1, 0, 0, 1, 0, 1. You would think the first immediate reaction to this thing is you would think that this is how -5 is stored. But guess what?
It's not.
It's not. Okay? This is not how -5 is stored. Not how -5 is stored. So now the question is, how is -5 stored? No. The first bit is always still the sign bit. Okay. Now here is why so we're going to learn how, but here's why I want to motivate why we're going to do it this way. Okay. Now, inside the CPU, there is some hardware that adds binary values. Are you with me? It adds binary values, and it has, the wires going, and so there's a wire. It's a combinational circuit. It's what we call a combinational circuit, and those of you who are in the organization class know what that means, but here's what we want to have happen. We want to use the same circuit to be able to add either signed numbers or unsigned numbers. So in order for that to work, and in order for it to work properly, what should you get if you add 5 and -5? You should get 0. So let's figure this out. Are you with me? Inside that circuit, the adder, when you add 5 and -5, you should get 0. We know now that 5 is stored how?
0,
0, 0,
1, 0.
0, 1, 0, 1. We know that this, and now, so here's my question. My question is,
What will get us 0?
Yes. The question is, what will get us 0, 0, 0, 0, 0, 0? That's the question. The question is, what do you have to add to this in binary to get all zeros? Now so can we figure this out?
Maybe.
So you need.
Okay, so tell me, let's start from the right. Let's start from the right. So,
1.
Need a 1.
so this would be a 1
And
here.
a 1 next
Another
to it.
1.
You would need a 1 here.
And another 1. No, sorry. Yes.
Wait, what do you need? 1 plus 1 is 0,
Yeah,
carry your
carry
1.
And then 1 plus 1 is 0.
0, carry your 1.
So it's 0.
So you'd need a 0 here, right?
And that would be 0.
And then a 1.
And it would carry the 1, so you need another 1.
And then a 1.
0, carry the 1.
So I need another one,
Yep.
And then another 1.
0, carry.
and then another 1.
So that's -5.
So this is how -5 is stored.
And then we get a 1 in the sequence.
And notice that, are you with me? So what we're saying, what we're claiming here is that -5 decimal equals 111011. 111011 binary.
Wow.
for a 6-bit cell. Now, can you tell me the rule? How do you go from whatever number, how do you figure out it's negative?
Is it,
It's the opposite.
is
of
it everything
but the last
inverted,
one.
but the first one is a 1 anyway? It's pretty close.
Well,
But it depends if it's even or odd, right?
yeah. Okay, are you ready for
It's
the
inverted until you hit.
something? Yeah, I mean, all these, you know, there's going to be a bunch of ones up here, and then something kind of happens, yeah. Can you figure this out? Huh? Can you figure out a little algorithm or a little rule of how this would, how on earth, what's the rule?
Well, if it's odd, then your number also has to be odd. Right.
Okay,
Well, anywhere there's zeros, we need a 1.
I think,
So we can
If the
carry
positive version has a 1, and then yours also has to.
okay, now watch this. Okay, now watch this. This is,
After the first one, you need to get to the first one, and then after that, it's opposite. But before then, anyway, for example, like starting.
yeah, but this is not opposite of this.
I'm saying
After
the-
that one.
After that one. It has to
Does
be the
that
opposite.
have to do with 32? Like 32 minus 5?
Oh.
Get 27, which is the value of the,
oh.
you like add them all out?
Well, okay, watch this. Are you ready for this, sports fans? Check this out. So we're going to, let's start with 5, right? 0, 0, 0, 1, 0, 1, right? Now let me ask you this. What would happen if to this, what would happen if I just took every single bit here and I inverted it?
Oh, I know what it is.
Okay, hold on. What happens if I just take, what happened if I took this and I inverted every bit? What would I have? I would have 1, 1, 1, 0, 1, 0, right?
But you'd be missing.
But, okay, so now, the thing of it is that if I add this, what am I going to get? I'm going to get 1, 1, 1, 1, 1, 1.
You're just getting 1 less.
Okay? But what would happen, so here if I do add here, like this, if I do invert. So, but now, what would happen if I take 1 and I add this? What am I going to get? 0, 0, 0, 0, 0, 0. Are you with me? We'll talk about the overflow.
And add 1.
So you invert and add 1.
So isn't that kind of what
That's
we
it?
said?
Is it?
I said we flip everything but the last one.
No, that's not inverting and adding 1, because what if this were, that's in for this case, but that's not the general rule.
If the invert was.
You add 1, it wouldn't,
invert was-
if it's even, that doesn't work.
Add 1 to the next.
If it's even, that doesn't work.
Okay,
And if it's
you would
even, you see what I'm saying? Yeah. Does everybody see the rule? Okay? So that's how you get a negative quantity.
Is it a coincidence for the top example? Is it just a coincidence that the bottom one adds up to be 59, which is 5 less than 64?
That's not a coincidence, and that is in fact how it works. Yeah, that was a good observation. Yeah? Okay, so let's see, is that the rule? So here in figure 3.8, we have a cell is divided to store signed quantities. The cell is divided into a magnitude and a sign, right? And here is the rule, what we just discovered. The neg operation is taking the taking the 2's complement. The not operation changes the 1's to 0's and the 0's to 1. Are you with me? So now the question is, what's the rule between neg and not?
Neg is not plus 1.
Yes. And so that is the rule, the 2's complement rule. The 2's, and this is called negating a number is called taking its 2's complement. And so the 2's complement rule is, the 2's complement of a number is 1 plus its 1's complement. So neg x equals 1 plus not x. In this particular example, negative 5 is 1 plus not 5.
Can we explain that a little bit more? So if we go back to the last slide, it says to negate the neg operation is taking the 2's complement.
That's terminology.
Right, but aren't you
And that's how you negate a number.
but meaning making it negative, right?
Yes, meaning making it negative.
Okay, but aren't you supposed to add one there?
No, they're not.
No, the not operation, the thing that we did over here, the thing that we did,
That's not.
the thing that we did here was taking,
That's not.
Neg. We just figured.
yeah, the thing that we did here, this is the not of this.
Right.
And then adding 1 to that is,
The neg.
well, we would have to add, well, actually, yeah.
It'd be that whole.
It's, yeah, to negate this, it's 1, 1, 1, 0, 1, 0, and then adding 1 to that, so that's 1, 1, 0, 1, 1, 1. So this is the neg, sorry, this is the not, and then plus 1 is the neg.
Okay.
Okay, over here.
So taking the 2's complement is essentially.
Is negating. It includes the adding the 1.
Okay.
Yeah,
That's what I was curious.
yeah. That's the terminology. All right? Good deal. We'll continue this next time. I guess we have Martin Luther King Day, right? No class on Monday. So see you Tuesday.